This video reviews the quantity electric current that we learned about in ninth grade. And I'll speak fairly quickly because I know you can pause the video. And when I ask you to fill in a blank, I'll speak right through it because I know you can pause the video then as well. All right, here's a diagram of a circuit, battery, light, motor, wires, and we have charge moving through the circuit. And you can think of it as the charge is filling every part of the circuit like water in a pipe and flowing like water in a pipe. We chunk the charge into 1 Coulomb bits, just as when we talk about water, we'll talk about gallons of water in the pipe, even though the water isn't actually physically grouped into gallons. Same with charge. Right, here's the definition of current. The current through, say, this light is the number of coulombs of charge that go through it per every second. Right, like gallons per second flowing through a pipe or flowing through a sink faucet, for example. All right, here's an example problem. Fill in the blank, pause the video. 12 coulombs in 3 seconds, what would the current be? How many coulombs of charge per second? Well, of course, it's 4 coulombs per second. So think about what you just did, add, subtract, multiply, or divide. Current has a symbol. See if you remember it from freshman year. It's I, capital I normally. So we can write the definition this way. Current, capital I, is defined as divided. So it'd be charge divided by time. So we write the symbols for that. Q divided by T. But this is a calculus-based class, so we could also talk about an instantaneous current if the current happens to be changing or fluctuating. The symbol for an instantaneous current is a lowercase I, just like that I, but lowercase. And this will be a derivative, so think about what that derivative would be. Pause the video if you have to. It's dq dt. That's the calculus definition of electric current. All right, the unit would be the coulomb per second as we saw, but it's been renamed. See if you remember that name from freshman year. It's the amp, which is short for ampere. That's a person's name. So the symbol for the ampere is a capital A. And notice current is a rate. It's an amount with respect to time. Amount divided by time as a derivative, it's dq dt. It's a rate. It's a time rate of change. How to measure I. See if you remember the name of the device we use in freshman year to measure current and the symbol for it. The name is the ammeter. It's from amp. It's like amp meter, but it's assimilated, so it's just called an ammeter. And the symbol is a circle for the device, a wire bringing the current in, a wire taking the current out, and a capital A for ammeter. The way it works is it will only measure the current that goes in through this wire and through the device and comes out this way. You have to run the current you're measuring through the device. Imagine there's a little counter in there counting coulombs as they go by and timing and doing the division. All right, the next note is on how to connect an ammeter in your circuit. And here's the general rule. Let's say we want to measure the current through this light bulb. Well, the exact same charges must pass through both the light bulb and the ammeter. No more, no less, the exact same charges. So I have two possibilities here, and you try to figure out in which circuit is the ammeter connected correctly, this one or that one. Pause and choose. It's this one. Here's the reason. An ammeter only measures the current going through it, and we want to know the current through that light. So we have to set this up so exactly the same charges go through both of them. The ammeter could be here after the light, or it could be up here before the light. It doesn't matter as long as you force the exact same charges to go through both. Kind of like having a bridge and a toll booth. Very similar to that. You can put the toll booth before the bridge or after the bridge, and you'll still count the number of cars that go through, and you could, or per day, for example, you could still figure out the number of cars that go through in a day, whether the toll booth is before or after the bridge. All right, now the next note is about what an ammeter has to be like as a circuit element. Well, we want to follow the general principle that the measuring device should not change the thing we're measuring. So you ask yourself, what was here before there was an ammeter here? On the previous page, what was here before when the circuit was working? And the answer is wire. There was just wire here. So when we replace the wire with an ammeter, we don't want that to change anything. We don't want that to make the current go any slower or faster. We want the circuit to think that there's still wire here. So that means an ammeter must be like blank, with a very blank resistance. See if you can fill those in. It must be like wire with a very low resistance. very low resistance. And this is why if you do hook up an ammeter like this, you can burn it out because the charges will get pushed from the battery, run through the ammeter like wire back, and you'll create a short circuit with the battery. The charges go very, very, very fast. If we were building real circuits in lab, this would be a worry, and you'd have to pass a little test to show me you won't hook it up incorrectly. But you'll be playing with a circuit simulator, so that won't happen. You won't actually break the ammeter. You have to know something called the positive current convention, and this often gets students angry. This is, and by the way, convention here means agreement. So you could think of this as the positive current agreement. The positive current agreement is this. We define current as the direction that positive charges move or would move in an electric field or in whatever's pushing the charges. So if we have positive charges moving to the right, this is called current to the right. If we have negative charges moving to the right, that's the opposite. That's current to the left. So if you think of having a positive plate here and a negative plate here, that creates a current to the right. Okay? If you think of, to make this happen, you have to have them reversed. The positive plate would have to be here to pull in the negatives and the negative there to repel them. And so we call this a current to the left. Current flows from positive plate to negative plate no matter what's doing the moving. You might ask, wait, electrons are the only thing that move in metal. Positives can't move in a metal. Protons don't move in a metal. Why do you even do this? Well, there are two reasons. One, this was all defined before they knew what moved in metals. It was defined in the 1800s and they didn't know. Second, there are cases where positives move, just not in metals. Very commonly in ionized gases like the ones in a fluorescent bulb or the solar wind coming from the sun, you have positives moving a lot in gases and plasmas. So it is the case that positives will move, so this is a useful definition. So in circuits, here's a battery. The long line means the positive plate. Current will flow away from the positive through the circuit elements and back into the negative. And in general, when we have circuits with simple batteries like this, simple one battery or two or three in a stack, I will draw it always following the same kind of pattern. All the batteries on the left, nothing but wire on the top and bottom, and all the circuit elements on the right in a vertical stack like this. That makes it easier to think about and analyze all the different things we have to look at in a circuit.